All right, so in this worked example, we'll be looking at a question related to the chapter on radioactivity from AICE Physics. And this question comes from paper 23 that was administered in May, June of 2015, question number 7, and it reads, the equation represents the spontaneous radioactive decay of a nucleus of bismuth-212. And they give us the equation there, and let's remind ourselves sort of what all this information is. So it's telling us that there's 212 nucleons in the nucleus of bismuth, and 83 of them are protons. And it's yielding some mystery chemical X, plus this is tellurium, and it has 81 protons and 208 total nucleons. And then this says plus 6.2, and the way we read this is mega electron volts. Mega electron volt. An electron volt is a unit of energy. And it's typically the unit of energy we'll use when we're dealing with sort of nuclear reactions, because a joule, the SI unit of energy, is a lot of energy. And so an electron volt is a tinier unit of energy that's is more reasonable for what tends to be the lower energies that are occurring at the atomic level. Now, ultimately, you can get to a lot of energy sort of out of nuclear reactions. I don't want to say that, but sort of individual sort of atom that's reacting may only release sort of a tiny amount of energy. But here we see it's in the mega, right? It's a mega electron. Explain the meaning of spontaneous radioactive decay. So this right here, these reactions are spontaneous, and that means that there's no way to sort of coerce them into going. You can't do anything to this bismuth to get it to, sort of break up like this. It just kind of happens on its own. And so we'd say that the radioactive decay is independent of external factors. You can't heat it up, you can't increase the pressure, decrease the pressure. There's nothing that you can do that's going to sort of get this to go, and that's what we mean by spontaneous. So it's unaffected by external factors, like heat and pressure. State the constituent particles of X. The constituent particles of X. So if we just keep track of the idea that the nucleon number is conserved, here we've got 83, and then it goes down to 81. So like we're missing 2 protons, right? Like this mystery X here, something with 2 protons. And the nucleon number from 212 has decreased to 208. And so we're missing, 4 total nucleons. And so we can sort of realize that X here, helium, right? This could be an alpha particle, right? So this might be a type of radioactive decay that we're going to sort of study in its own right, or you may have already sort of previewed by going through the slides. This is alpha decay, where a nucleus emits an alpha particle, which, remember, the helium nucleus has 4 total nucleons and 2 of them are protons. So anything with 2 protons is helium, right? Now they want the constituent particles of X, and so let's say 2 protons and 2 neutrons. Those are the constituent particles, right? So we wouldn't just say an alpha particle, like X is an alpha particle. What is that? It's 2 protons and 2 neutrons. Use the conservation of mass energy to explain the release of 6.2 mega electron volts of energy in this reaction. So the conservation of mass energy is something that we've sort of talked a lot about this year, that the quantity mass energy is conserved. And so here we kind of see that basically the energy that it takes to bind this bismuth together, some of it is sort of released as this undergoes this radioactive decay. And so radioactive sort of decay reactions can release energy. It really is grounded in Einstein's famous theory, equals mc squared, where if the mass is a little bit less, okay, when we atom up or when we sort of break something down, that what we call a mass defect, okay, a slight change in mass shows up as energy, okay, and so this is how we can sort of liberate energy. And it's sort of like, well, that energy used to be sort of in here, and it was the energy that kept this bismuth atom bound together. And so when it decays, it can release, some of that energy, because the energy is no longer needed sort of inside the molecule to bind it together. It's like the binding energy of bismuth here. As it undergoes this alpha decay, this much energy is liberated. So you'd want to kind of put that into your own words. You know, some amount of mass is being converted, you know, into energy. Or you could even reference like the binding energy of bismuth is greater than, you know, the binding energies of this alpha particle in this tellurium. And so because energy is conserved, mass energy is conserved, we need to account for sort of that energy release. Now it says calculate the energy in joules released in this reaction. And so we need sort of a conversion here, and really it's just defining an electron volt. And so an electron volt is the amount of energy that an electron gets when it's passed through a potential difference of 1 volt. So like if we accelerate an electron sort of in an electric field, and that potential difference between the two plates is 1 volt, then the energy that it takes to sort of push that electron against the field, the energy that the electron would sort of develop as it moves through the field would be 1 electron volt. And we know that the charge on an electron is 1.6 by 10 to the negative 19 coulombs. And so if you just remember the value for elementary charge, or you look it up, remember that these AICE papers give you that data, then we can just sort of use that as a conversion. And so if we start with what we're given here, 6.2 mega electron volts, we're going to cancel out, we can deal with the mega right away. Let's just go. 6.2 mega electron volts, right? So mega just means million. So we got 6.2 million electron volts. And now we can cancel out electron volts and go to joules. There is 1.6 by 10 to the negative 19 joules per electron volt. And again, that's just because of the way that we sort of define the electron volt as the times right there. As you know, the energy that the electron gets as it passes through a potential difference of 1 volt. And so if you kind of recall the physics of electric fields, we said that the electric field strength was the force per charge, or it was the volts per distance, right? So this is how we define sort of the electric field strength. And then remember that voltage is the energy per charge. So we can rewrite this as energy equals the voltage times the charge. And that's really the key right there with making sense of sort of this conversion. Energy that the electron gets as it passes through a potential difference of 1 volt is equal to, you know, one electron volt, right? And we just multiply that 1 volt by its charge, which is 1.6 by 10 to the negative 19. And so it's a simple conversion to say, well, then that's the number of joules in an electron volt, right? Because it's multiplied by 1 volt, right? So charge times 1 volt equals the energy of an electron, 1 electron volt. And so the conversion is just to take the 6.2 million and multiply it by 1.6 by 10 to the negative 19, right? The number of coulombs of charge in an electron or a proton, or also the number of joules as we define an electron volt. We got 6.2 by 10 raised to the 0.2 by 10 raised to the 6 times 1.6 by 10 to the negative 19, and we get a calculated value of 9.92 by 10 to the negative 13, which we could maybe, come on, let's just well, 9.9 by 10 to the negative 13. And I think the question goes on maybe to say, usually it says how many total marks there are. Anyway, that's the end of that sort of question. So that's all that you would have for radioactivity, you know, on paper 3, you know, just like this question. So that was the one from, you know, this year.